last speaker of today is Xián García Veiga from the University of A Coruña. And he's going to talk about algorithm optimization on GPUs, analysis of synchronization techniques using Fast Fourier Transform as a case study. Thank you.
Gracias. So, good afternoon. First of all, thank you to Do It Now for the invitation. I'm currently a student at the master which Jorge is a professor at. And I belong to the computer architecture group at this university. And together I want to present my current master thesis that I'm working towards in the master, which is co-directed by Margarita Amor. And the presentation is about algorithm optimizations on GPUs, trying to analyze synchronization techniques using the Fast Fourier Transform as an example for the presentation. I want to do a brief introduction, then introduce a little bit of concepts about CUDA, then talk about the Fast Fourier Transform, to then dive into the implementation we've done with cooperative groups, then the optimization using warp-level primitives, and finally, some tools that help me on the process. At the end, I also want to share our experimental results that we obtained. So, as you may know, GPUs were originally used to accelerate computer graphics, but with the advent of compute shaders and floating point support, people started noticing that they were quite useful for accelerating other kinds of computations. Fast forward to today, we now have heterogeneous systems where we have different devices for different purposes. So, for example, we have GPUs, which are low latency devices, very good at sequential tasks, lots of branching, but they have low core counts. And on the other hand, we have GPUs, which are high throughput devices, are very good at parallel tasks, and have tens of thousands of cores. We also have our accelerators, like neural processing units, FPGAs, etc. But I'm going to focus today on GPUs. Because many of the HPC tasks are data parallel problems, which means that running them on the GPU can provide significant performance and throughput gains. One of those workloads is the Fast Fourier Transform, or FFT for short, which is what I want to present today. However, programming in GPUs, it's sometimes a little bit difficult because it has a different mindset that we are used for CPUs. And for starters, programming languages and frameworks are a little bit different. The most common ones are CUDA for NVIDIA GPUs, ROCm for AMD, and then we also have SQL and OpenCL, which are a little bit more generic and try to work with multiple types of devices. CUDA, it's one of the most popular GPU frameworks, and it's the general purpose GPU compute hardware and software platform made for NVIDIA GPUs. It divides its code in two parts, one that is dedicated to the host, which is run on the CPU, and another section of code that is run on the GPUs, which can be multiple and communicate back to the CPU. This is pretty good because as programmers, we can choose where we want to run our code. For example, if it runs better on CPU, has a lot of branching, we can do that, and then offload some more heavy compute demands on the GPU. But it also means that we have normally two separate memory spaces, which there are frameworks and there are exceptions. There are now some chips which have unified memory. But in normal HPC clusters, if we want to get the most performance out of this, it's something we have to manage ourselves. So a CUDA GPU is composed of several streaming multiprocessors, or SM for short. Each SM is divided into several partitions, as we see here in this diagram on the right. This is actually a diagram based on the Ampere architecture. And well, we have multiple blocks, like instruction cache, a warp scheduler, dispatching, a register file, load store units, special function units, a tensor core, which is used to accelerate small matrix to matrix multiplications, and finally, general purpose cores, which are arithmetic logic units for both integer and floating point calculations, And we have several of them. We have several cores. Each core can be running several threads at once. And, well, this is a good thing. I will talk a little bit about it later, more in detail. And we also have several memory types. We have a register file. We have constant memory, shared memory, level 1 and level 2 caches, and finally global memory, which is usually the memory that we see separate to the chip on the board. So CUDA follows a single instruction multiple thread model, which essentially combines single instruction multiple data with a single program multiple data. Essentially what this means is that threads are grouped into small chunks called warps, which run always simultaneously. And whenever one set of threads reaches a memory transaction or another operation that takes a long time, the hardware can switch its execution to another group of threads. So this allows us to hide effectively the memory latency. This operation is done automatically in hardware at no cost. And, well, it's quite useful because then we can get a little bit more performance and not having to wait for the memory or the compute hardware to be available. From the point of view of the programmer, this execution model translates into that we have several groups of threads called warps, which is the fundamental execution unit. In all NVIDIA architectures up to this date, it has always been 32 threads. There have been some rumors that maybe it will change in the future, but so far it's always been 32. These warps are grouped into blocks, which blocks are executed at the SM level, and one block, once it enters as an SM, doesn't exit it until it finishes its execution. Then we also have the grid level, which is one GPU, and multi-grid, which would be several GPUs in a cluster. This is important to mention because communications between different levels of the hierarchy must use different types of memory, which is an important consideration for programmers. The number of threads that we can run simultaneously is limited actually by the resources we have in the GPU. So for example, registers, the register file that we had in the beginning has to be split between all of the available threads. So we should not exceed this number. And the same happens for shared memory. This process of selecting the number of threads is quite complicated, not a trivial task, and normally is done by auto-tuning, essentially running benchmarks on your own code with different parameters and choosing the most performant one. In terms of memory, at the thread level, we have registers, which are the fastest memory available. A register file, as I said, is divided into several blocks between all of the threads. We have a hardware maximum of 255 threads, registers per thread. And if they do not fit, because of our code, it can spill back to global memory and also be cached in level 1 or level 2 caches as a consequence. At the block level, we have shared memory, which in modern architectures is actually has a split that is configurable between level 1 and this shared memory. So as the programmers, we can choose how much memory we want to allocate for each purpose. It is divided in banks, and this is important because as programmers, we want to access consecutive banks from consecutive threads. Otherwise, we can get into a bank conflict, which means that operations have to be serialized, so we lose performance by doing that. And finally, at the GPU level, we have global memory, which is the normal memory of the card. It is several gigabytes in size. And also, we have a special kind of memory that we can use, which is constant memory. It's originally designed for 3D graphics purposes. It's read-only from the device. It has to be initialized at compile time, and it also has to be, its data has to be copied from the CPU, so we cannot interact with it directly on the GPU. And it also has broadcast-like access. So if one thread or multiple threads try to access the same memory location, that works fine. But if we have to access multiple, those requests are serialized, so we have to be careful. Now that I introduced a little bit about CUDA, I want to talk about the Fast Fourier Transform, the algorithm. So it's a fundamental operation in a lot of applications. So for example, signal processing, differential equations, simulation, image, video compression, it's everywhere. The Fast Fourier Transform is defined using this formula. And we can rewrite it into several patterns depending on our requirements. So one of the most common ones is the Culley-Tukey, which is especially useful in CPUs because it takes great advantage of cache locality. And we also have Stockham, which is usually best suited for GPUs. We also have other formulations like the piece, also called in place. But I'm going to focus on these two first ones. If we take a closer look at the structure, we have a divide and conquer strategy where the fundamental operation is called a butterfly. This butterfly takes several input elements of a discrete signal and performs a calculation returning the same number of elements as output. This number of elements is actually called the radix. So in this example at the right, we are using radix 2 for simplicity, but we could use radix 4 or radix 8, depending on our requirements and how we need to optimize the algorithm. Also important to note is we have the twiddles, which are constant factors, which are this expression right here, used on each step. It basically consists of the complex circumference being divided into n chunks, n being the size of the FFT transform. This is important because we can actually store them on constant memory, but as we saw experimentally, this is not really worth it as some reads get serialized and it doesn't give us much performance. So the Culley-Tukey pattern follows a bit reversal step, which is basically a reordering of the data, followed by the second logarithm of n being the size of the FFT. So the reversal step is highly memory bound. Then we have several steps, which we increase the stride up until we mix, let's say like that, all of the data points with each other, and we obtain the final result. The Stockham pattern is similar, but it combines the bit reordering step into all of the different phases. So we get a more complex data pattern at the expense of having one less step. So now that we saw how the algorithm works, how would we implement it in the GPU? So as each smallest operation is a butterfly, we take that one thread computes one butterfly. We try to store the values in registers because they are the fastest memory available. And in order to interchange data following that pattern, we need synchronization. The traditional wisdom would be to use the operation sync threads, but this implies waiting for the entire block, which can introduce a delay, or maybe we are forcing all of the warps to reach the same execution point, even though we really didn't want that, giving us some inefficiencies, as you can see in the diagram on the right. So to solve this, we used the cooperative groups API, which is NVIDIA's own thread synchronization API, introduced from the Volta architecture onwards, and CUDA 9.0 back in 2017, which was a while ago. This API allows us to do these data communications on the warp, block, grid, and multi-grid levels, essentially all of the levels of the hierarchy. We have directives for group creation, like tile partition, but there are many more. It's just the one that I used in this example. We have operations for data interchange between threads, such as shuffle, so shuffle operations, and finally synchronization from that group. The advantage of this is that at the warp level, it does not require sync threads, so we can synchronize a single warp instead of having to synchronize the entire block. And it also does not require shared memory, so we can spare it for other uses. Here at the right, I have a diagram of how it would look like being implemented with cooperative groups. So we have smaller groups, we synchronize them, data interchange, and then we create a bigger group. This is for the Culley-Tukey pattern. Stockham would be similar, but with a fixed group size. Well, cooperative groups, it's pretty wonderful. It's flexible, it's portable, it's really easy to program, and abstract the entire hierarchy. What more could we want? But the problem is that we saw is that it leaves some performance of the table. So we could optimize more. When we dove into it, we found out that we could use warp level primitives which are essentially intrinsics that allow us to do operations at a lower level. The disadvantage is that they are optimized for specific purposes. They are not portable between hierarchy levels. We will need to design another approach for the different levels. They are quite difficult to program. They are only available at the warp level. But we get a lower number of hardware instructions. So as a side effect, we get slightly better performance. Here I have put an example of a similar region of code where you can see cooperative groups is pretty readable, but with warp level primitives, we have masks and everything, and it's pretty complicated. So I wanted to give some divulgative aspect to this talk, and I wanted to include some tools that helped me in the process to find these optimizations. So first, I want to talk about Compute Sanitizer, which is NVIDIA's own functional correctness checking suite. So it helps you to check for memory initialization, out-of-bounds memory accesses, race conditions, and invalid synchronization with these commands I put right here. I found this really useful because normally I see people debugging with printfs, and sometimes you increase the number of threads, and then your code doesn't work anymore, and you don't know why. And you spend like 2 hours debugging it, when you could use these tools, and it tells you exactly, well, you have a out-of-bounds memory read, and it's pretty helpful. I also consider it pretty useful to run this entire suite before you consider a program finished. So although you think everything is correct, everything works fine, you should always run this to see if you get any error back. And also put the flags for the compiler to give an error if anything small appears. And also pretty useful because we always forget about this. It warns you about free calls, which as C programmers usually happens. Another tool that helped me a lot is Inside Compute, which is the interactive profiler used for CUDA programs. It's pretty useful because if you have administrator access, it gives you access to hardware performance, counters, and metrics, which gives you very detailed reports. I put here an example of the roof line, which compares memory alongside compute throughput, and it actually gives you pretty verbose recommendations of what you should do. In my experience, you should take this with a grain of salt because it might tell you to optimize for something, you do that thing, and then it tells you about the contrary. So you must be careful to not overdo it. Take the advice, but think it through, and then choose the best option. Here at the right, I also put the memory chart, which is pretty visual. It helps you locate all the memory transactions, speed, sizes, and it's pretty useful. Also, there's the occupancy calculator, which helps you with this process I told you earlier about using the optimal number of threads for each application. But this has to be, again, taken with a grain of salt because it tells you about the code you're running. But if your code changes due to execution parameters that may vary, you may need to adjust this practically depending on your exact application. And here as well, I also put a screenshot of the assembly view, which was pretty useful for me for the warp level instructions to see the number of instructions generated, the number of registers used, instructions executed, and even dependency between registers, so you can maybe move some operations to get a better execution. So finally, with all of this, we want to share the performance that we obtained. We measured this in an NVIDIA Tesla T4, and we found that the alternative with warp level primitives achieved a slightly better performance, about 2%, which is not much, but is when you want to optimize for every droplet that the hardware gives you, well, it's what you can get. We found that comparing it to QFFT, which is NVIDIA's own FFT library, we obtained higher performance in all of the cases up to n equals 64 with the Cooley-Tukey and the Stockholm pattern as well. We calculated the performance using this expression, which is pretty common for FFT performance measurement. Looking at the same in terms of speedup, we see that Cooley-Tukey and Stockholm obtain similar performance of both platforms, and we obtain a maximum of 13% of speedup. Here we see that, well, performance varies a little bit across the implementations, but is something that, well, it depends. As final conclusions, I wanted to say that, well, GPU programming is not easy, and that there are appearing more and more frameworks that make it more accessible to normal programmers, such as OpenACC, which allows you to program with programmer directives and actually port your code to GPU easily, CuPy and Triton, which are frameworks for, well, similar to NumPy, and Triton for machine learning applications. And from NVIDIA itself, there are a set of libraries like CAP, Thrust, and libcuda C++, which help normal programmers to implement, to have easily accessible intrinsics and algorithms in a similar way to the C++ standard library. And finally, there's also NV shared memory, which helps you communicate different GPUs using an MPI-like interface. In conclusion, what I wanted to say with this is that understanding of the hardware, how it works inside, is important in order to maximize performance and get the most out of our GPUs. We say optimization using the FFT as a case study, first using cooperative groups, and then trying to optimize it using warp-level primitives. And we achieved up to 13% speed up for sizes less than 64. As future work, we want to develop this for higher FFT sizes, so it's more usable in more applications, because 64 is quite a small size. We want to do optimizations of more hierarchy levels to scale this up. In fact, our next objective is interword communication using thread block clusters, which is a normal feature introduced in Hopper architecture, I think. And we also want to see if this can be applied, these methods, to other algorithms. But this is still future work that we are, well, working right now. And thank you very much. If you have any questions, I'll be happy to answer them.
I am assuming that this was one-dimension FFT?
Yeah.
So have you done already the work on multidimensional 2D or 3D?
No, not yet.
And then the other question would be, have you tried mixed precision?
Sorry?
Have you tried mixed precision?
Mixed precision?
Yes.
No, we haven't tried it yet.
Was this a single precision, FP32?
Yeah, we tried with doubles as well. Yeah,
Okay.
Now that you mention it. And we obtained similar performance. In A100, in fact, it was pretty similar because it has more double compute units. But in consumer GPUs, which is what we have more accessible, it actually decreases performance a lot.
Right, and then the final thing is you should try this on there's one sub-benchmark in the HPC challenge that is a 3D FFT, and then run it in a distributed fashion.
Okay.
So you have a 3D transpose also as one of the steps. It's an additional challenge. And let's see how good it gets in terms of scaling. Leveraging also network topologies, both scale up inside, leveraging NVLinks, and then scale out, leveraging InfiniBand.
Yeah, the idea behind this is working from the bottom to the top. So we are still beginning at the...
Good luck with it.
Yeah. Okay, thank you.
Questions?
This is one really easy. There is a direct relation between the cores and the warps, or the warps are an abstraction of the...
The warps are groups of threads. Threads is a... Yeah.
But what I mean is how they are related to the hardware. If they are related.
Yes. Well, cores are essentially the hardware that threads runs on, and threads switch. So we have on the same cores multiple threads running at the same time. The register file is partitioned, so they are interchanging. So it doesn't have a real mapping from the cores to the threads. Threads are running on the cores, but the hardware can change them whenever it wants. So this change of threads is not controlled by the user, by the programmer. It's done automatically in hardware, depending on the resources available. I don't know if that answers your question.
I suppose that there is no really direct relation between the cores and the warps. This must be abstracted.
concept of warp, it's basically an architecture feature on the NVIDIA GPUs. The way you have to think about this is you have a computational problem, which is set of number of operations, and you will associate this to a particular physical core, how many operations you want to do, and that will define a set of tasks. Then the hardware will grab tasks in groups. That group size, it's an architecture feature, and that's what we call the warp.
Okay, any more questions? Yes.
I have a couple, but let me start with the first. And again, Jordi, you say stop, and I stop. First, NVIDIA recently started providing two different flavors, they call it like this, of module drivers, the privatively and the open. Did you find differences when you use one and when using the other with the same hardware, or?
We haven't really tried the open source driver because all of this was run on a supercomputer which has the official NVIDIA driver. So we really haven't explored.
Both are official NVIDIA, and they are both provided by NVIDIA, and they are both in NVIDIA repositories.
Yeah, but we just ran with the driver that was available in the supercomputer. We didn't have the option to change it. So,
okay,
yeah.
so, and probably the answer to the next one will be, also recently in the new drivers, NVIDIA provides this feature, they call it direct storage, that it's supposed to communicate directly to NVMEs. And also there's this new thing, this persistent daemon, that handles the way that jobs see the driver and the hardware differently. Did you find any advantage when in any of those two new things? Thank you.
Well, this always assumes that the data is already loaded in memory because we assume the FFT is part of another complex process. And yeah, we're already working on the GPU memory, so we haven't really explored options about data loading because this is intended as when you have your complex algorithm, you integrate these routines into your program. It's not like a program by itself to compute FFTs. Really, that was the focus. So no, we haven't explored data movement or even direct data reading from GPU.
Not the persistent, sorry, the direct, I don't remember exactly the new driver thingy. This daemon that controls, there's a new daemon that controls the jobs, that it's apparently, it used to be optional, but now it's provided, but it's not activated.
No, I don't
okay.
really, we haven't really worked with that, at least yet, because we focused on the compute element, not the support system, anything like that.
Okay, thank you.
I'm sorry.
Any question over there? No? Okay. So thank you so much.